We are starting chapter 24, the final chapter of Math SL, normal distribution. Starting with a lot of reading here, page 630. In chapter 23, random variable x in a binomial probability distribution could take on values 0, 1, 2, 3, comma, dot, 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 all the way to n. For some finite n, which is an element of the natural numbers. Remember, the natural numbers are integers, positive integers. For a continuous random variable x, x can take on any real value. In this case, the probability can be defined by a probability density function instead of a probability distribution function. They are similar in that if you find the total area of this function, it adds up to 1 in the same way that the individual probabilities in a probability distribution function added up to 1. If the domain of the function is a is less than or equal to x is less than or equal to b, then integral from a to b of the probability density function f of x dx is equal to 1. The probability that fx lies in the interval x is between c and d is the probability is c is less than or equal to x less than or equal to d, and that's equal to the integral from c to d of f of x dx. So this first integral is when you're integrating over the entire probability density function. If you integrate over the entire probability density function, of course you're going to get an area of 1 because that's the definition of the probability density function. But if you're going to just integrate from between two values c and d, then you're going to get a part of that 1. It might seem strange at first, but in the continuous random variable case, the probability that x can equal a particular value is 0. So the probability that random variable x is equal to a certain value x is 0. For this reason, what can we say about these expressions? Probability that c is less than or equal to x is less than or equal to d, c is less than or equal to x is less than d, c is less than x is less than or equal to d, c is less than x is less than d. And you can see the differences between these as I've interchanged less than or equal to with less than, because sometimes that makes a big difference in math, right? But in the case of probability density functions, since the probability that the random variable is going to take on exactly a certain value is 0, then it doesn't matter whether you put less than or equal to or less than for a probability density function. You remember for a probability distribution function in the last chapter, it did make a big difference if you said less than or equal to, right? Because each integer data value had a certain amount of probability that it would occur because the outcomes were discrete. But now that the outcomes are continuous, that's not true. Okay, so we can say that they're all the same. Okay, 24a, normal distribution. Page 631, reading. Give 3 examples from your life of variables which have normal distribution. So, let's see. How about the SAT test? The SAT exam. What else? Height of EAC students. In a certain grade. Okay. What else? GPA of high school students. Pretty much anything kind of complicated is going to give you a normal distribution. Okay? Write the probability density function for the normal distribution. Here is the variable x, right? That's the random variable x. So you can see that it is an exponential function, but instead of just being a regular exponential function, it's an exponential function with a squared variable. So it's not going to look like a typical exponential function. We're going to see what it looks like later. There are several transformations going on here. You can see that, like, there is a, look at this. This would be a horizontal translation, right? This minus mu. There's a division here by sigma, which is going to be a horizontal stretch, right? So there's these two transformations going on. We'll see how that affects the probability density function for the normal distribution. So this is valid for the random variable x taking on values between negative infinity and infinity. That sounds kind of crazy, but we'll see what that means. Where mu is the mean and sigma squared is the variance of the distribution. We write random variable x is distributed as the normal distribution with a mean of mu and a variance of sigma squared. The variance is the standard deviation squared. Page 632 reading. The normal curve is symmetrical about the y-axis, about x equals mu, and as x approaches positive or negative infinity, the curve approaches the x-axis as an asymptote. Okay? The height of the normal curve at x equals mu is 1 over sigma square root 2 pi. If I describe the shape of the normal curve, the normal curve looks like a bell, and actually it's often called the bell curve. Remember, it said that as x approaches negative infinity or infinity, the bell curve approaches the x-axis as an asymptote. So as it goes to the left and right, it kind of does that, right? The other thing we know is that x at mu, when x equals mu, that is a line of symmetry of the graph. So basically it looks kind of like that, a bell which extends out in both directions. By differentiating the normal curve once, then twice, we know that the maximum of the function is at x equals mu, and the inflection points are at mu minus sigma and mu plus sigma. And it's actually not that hard to differentiate this function here, but when you do, you'll find that the critical points, the inflection points, are at mu minus sigma and mu plus sigma. And what do we mean by that? So like if we look in here, you can see that this is kind of curvature concave down, right? And this part here is concave up. Well, at what point exactly does it transfer from being concave down to concave up? Well, it happens to be at this point, which is mu minus sigma. Okay? And then, same thing here. Where does it happen here? It happens at mu plus sigma. Okay. Page 633 reading. What percentage of values lie between mu minus sigma and mu plus sigma? Well, the answer is 68%. And we're going to see later there's something called the 68-95-99 rule. And what that says is that between the first two sigmas, you got 68%, which is quite a bit of your data points. And then between negative 2 sigma and positive 2 sigma, you got 95%. And then finally, between negative 3 sigma and positive 3 sigma, you got 99%. Okay, so the bell curve has most of its population pretty close to 1 sigma away from the mean, and then 99% are within 3 sigma of the mean. Okay, page 634 reading. See example 1. Then you're going to go to problem 1. Draw each of the following normal distributions accurately on the one set of axes. Okay, so here's just an example of a normal distribution, and the marks here indicate how many sigmas. Okay, so we said that 68% of the data is between negative sigma and positive sigma, And then we said that 95% are within 2 sigma, so that's 95%. And if you conclude one more sigma, that's like 99%. Okay? Draw each of the following normal distributions. So the first normal distribution is it's centered at mean 25 and it has a standard deviation of 5. So let's see, we're going to first of all mark our axes. So 0, 10, 20, 30. The other thing I need to mark on here is the height of the normal distribution. And remember that the height of the normal distribution is given by 1 over square root of 2 pi times sigma. Okay? And guess what 1 over square root of 2 pi turns out to be? It's really close to 0.4. Okay? Because 2 pi is 6.28, right? Square root of 6.28 is about 2 point something. 1 over 2 point something gives you something like 0.4, right? So it's 0.4 over sigma. We're going to use 0.4 over sigma to determine the height of the normal curve at the center, or at the mean, mu. So for the first one, it's going to be 0.4 divided by 5, and that's going to be 0.08. For the second one, it's going to be 0.4 divided by 2, which is about 0.2. And finally, 0.4 divided by 10 is 0.04. So actually, when we're going to map the heights here, we're going to make the tallest one 0.2, and then this will be 0.1. Okay? So that's going to help us map each one of these. So first we're going to do A, and we're going to mark that one in red. So the mean, the center, is going to be at 25, right? So I'm going to mark 25 here as the mean. The height is going to be 0.08. So 0.08 is about that tall, right? And then the standard deviation is 5. So most of the data is here within 5. And then it gradually moves out here. So here's 5. Here's 1 standard deviation out. Here's 2 standard deviations out. And here's 3 standard deviations out. Okay? Alright, so that is A. Now, B, I'll do in blue. B is centered at the mean of 30, and it has height of 0.2. It's really tall. You're like, why is this one so tall, right? And then standard deviation is 2. So 2 away, that's like 68% of the data right there, right? And that's when the curvature starts changing. So this is going to be 95% of the data. I probably need to draw it a little bit more down like that. And then finally, the rest of the data would be here. Okay? So it's a little taller because it's narrower. Remember that the area of each one of these curves has to be the same. It has to be equal to 1. So if you have a wide curve, like the red one, then it's going to be shorter. And if you have a narrow curve, like the blue one, then it's going to be taller. Now what about C? C is going to be in green. It's going to be centered at 21. And the standard deviation is going to be 10. So, wow, that's like really far away. The standard deviation is really far away. And the height is 0.04, which is just like that high. So, you can see that the green one is the most spread out of all. Okay. Makes sense, right? That the green one is so short because it's really spread out. Alright, moving on to page 2. 3. State the probability that a randomly selected normally distributed value lies between sigma below the mean or sigma above the mean. Well remember, we know the 68, 95, 99 rule. 68 means between 1 standard deviation to the left and 1 standard deviation to the right. 95% between 2 standard deviations to either side, and 99% 3 standard deviations to either side. So, the probability that a randomly selected normally distributed value lies between 1 sigma below and 1 sigma above the mean would be 68%. The mean and the value 2 sigma about the mean. Okay, so this is a little bit trickier. So it would be this section or this section. Remember that this first section is going to be half of 68%. It's going to be 34%. And then the next portion here, this is going to be, let's see, 95 minus 68, which is going to be 25, 27. It's going to be half of 27, which is 13.5. You're going to get used to these values pretty soon. So actually it's 34% plus 13.5%, which is 47.5%. 47.5%. Okay. So the second one, what we're calculating is this here. Between this and this. Okay, 2 standard deviations to the right. Okay, number 5. The mean average rainfall of Claudona for August is 48 millimeters with a standard deviation of 6. Over a 20-year period, how many times would you expect there to be less than 42 millimeters of rainfall during August in Claudona? Okay, so let's see. 48 is the mean. Standard deviation is 6. So one standard deviation to the right is going to be 48 plus 6, which is 54. One standard deviation to the left is going to be 48 minus 6, which is 42. Let's see. Over a 20-year period, how many times do you expect there to be less than 42 millimeters of rainfall during August? So that would be this section here. That would be, let's see, this section here is going to be half of 68%, which is 34%, right? And then the whole half is going to be 50. So 50 minus 34% gives us 16%. So this red region here is actually 16%. So the probability is 16% that you're going to have less than 42 millimeters. And what they're asking for here, over a 20-year period, how many times would you expect to be less? They're asking us for the expected value. So it would be 20 years times 16% is the probability, and that would be 3.2 times to be less than 42 millimeters of rainfall. So they combined this normal distribution problem with probability problem from last chapter. 7. The weights of babies born at Prince Louis Maternity Hospital last year averaged 3 kilograms with a standard deviation of 200 grams. These are kind of difficult when they mix units like kilograms and grams. You have to remember that you need to convert one or the other into the other. So like in this case, let's make everything into kilograms. So the mean is going to be 3. The standard deviation of 200 grams, what is that in kilograms? It's equal to 0.2 kilograms. So to the right, we're going to have 3.2. To the left, we're going to have 2.8. Okay, and then 3.4 here. Okay. Then it says, if there were 545 babies born at the hospital, estimate the number that weighed less than 3.2. Less than 3.2, that would be this region here. So that would mean half of this is 50%, right? Plus this region here, which we know is half of 68, 34. So it's going to be 50 plus 34%. It's going to be 84%. Okay? And then it says, what about, oh, I'm sorry, I'm supposed to multiply that times 545, right? Because it's 545 babies times 84%. Let's see. With the offline calculator, I'm going to do 545 times 0.84. And it's 456. 458 8 babies. Okay, and then it says, what about between 2.8 and 3.4? Let's see, between 2.8 and 3.4 would be from here to here. So this has, the middle part is going to be the 68%, right? The middle center part is 68%. Plus, there's this part here, which we know is 13.5. So we know it's 68 plus 13.5, which is 81.5%. And we know that it's times 545 babies. It's going to give us 444 babies. Okay? All right, moving on to number 9. The weights of Jason's oranges are normally distributed. 84% of the crop weighed more than 152, and 16% weighs more than 200. So remember, 16% corresponds to this region here, right? So 16% weighed more than 200. And 84% is, which corresponds to everything except for this 16%. So like this part corresponds to 84%. Weighed more than 152. Then it says to find mu and sigma. And you see how, since they gave us these very familiar values for the percentage, we already know that they're giving us values which are borders for standard deviation. So we already know that one standard deviation to the left is 152, and one standard deviation to the right is 200. So what is the middle value? So that would be halfway between 152 and 200, which would be difference of 48. So we would add 24 to 152. It would give us 176. So now we know that the mean is 176. So the mean is 176, and the sigma is going to be the distance between 176 and 200, or 176 and 152, which is 24. What percentage of the oranges weigh between 152 grams and 224 grams? Let's see, 224, that would be down here, right? So how many of the oranges are going to be this section, and this section? So that's going to be 68%, which is the middle two sections, plus 13.5%, which is the other section. And let's see, 68 plus 13.5 is 81.5%. That sounds familiar. We saw that before in problem 2. Okay. Number 11. Do you see how we're getting a lot of answers here because they just happen to be asking for percentages of population that's between exactly standard deviation values. And we know the standard deviation values convert to percentages of 68, 95, 99, right? The heights of 13-year-old boys are normally distributed. 97.72% of them are above 131 centimeters, and 2.28% are above 179 centimeters. Okay, so let's see, 179 centimeters. 179. Actually, we know this is this value here is like, it corresponds to the outside standard deviation values here. Remember how the middle section here is 95%, right? The middle 4 sections is 95%. So the outer sections are going to be about 2.5% each. It actually happens to be 2.28%. 68, 95, 99 sounds very catchy, but it's an approximation. Okay, so 2.28% are above 1.79. So that means this last standard deviation value is going to be the 2.28%. 97.72%, which happens to be 100 minus 2.28%, are above 131. And so that's going to be these people here. Okay. So, we know that this marker is 131. This marker is 179. So, can we figure out the mean now? Yeah, because it's halfway between 179 and 131. It's going to be about 48 plus 131, which is going to be 179. Oops, not 179. 24 plus 31, which is going to be 155. Okay. And then each one of these divisions is going to be a standard deviation of 12. Okay, so the sigma is 12. The mu is 155. A 13-year-old boy is randomly chosen. What is the probability that his height lies between 143 and 191? Okay. So 143 is right here. 191 is like one standard deviation more over here. So like, that's pretty much, this area here is pretty much 50%, right? This orange area is pretty much 50%. And then 143, that's about 34%, right? Because it's half of 68%. So let's just, to find this, let's just say 34% plus 50%, which is 84%. Okay? We don't even need to worry about this part here that's not counted because it's like really small. Okay. Finally, number 13. A bottle filling machine fills an average of 20,000 bottles a day with a standard deviation of 2,000. So the mean is going to be 20,000. And the standard deviation is 2,000. So this is going to be 22K. This one's going to be 18K. Assuming that the production is normally distributed and the year comprises 260 working days, calculate the approximate number of working days on which under 18,000 bottles are filled. So under 18,000, that would be this section here. And we know that this section here is equal to 50 minus 34%, which is 16%. Okay? Remember that, again, this is 34, this is 34, because they add up to 68, right? Then this part here is 13.5, and this part here is about 2.5. 13.5, okay, etc. Okay? Over 16,000 bottles are filled. 16,000 would be here, right? So 16,000 bottles are filled is going to be 50%, this 50% here, plus 34% plus 13.5%. Okay, so that's going to be 50 plus 34 plus 13.5, and we get 97.5%. Finally, between 18,000 and 24,000 bottles are filled inclusive. So that would be this section here is 34, this section here is 34, and this section here is 13.5. So let's do that. We're going to do 34 plus 34, which is 68, plus 13.5, and that gives us 81.5. Okay, so that's it.